Let's talk about what's coming tomorrow in our series on supervolcanoes. But first, we need to travel back in time about 74 million years. The year is 66 million BC. A small asteroid or comet strikes Earth near the Yucatan Peninsula, triggering an extinction event that wipes out the dinosaurs. It's been 20 million years since the breakup of the supercontinent Pangaea, and Earth's land masses are drifting into new configurations. New species are just beginning to fill the niches left empty by the mass extinction. And life on Earth is recovering when suddenly, with one fell swoop, it all comes crashing down again. Not because of another extraterrestrial impact, but because of something much closer to home, a super eruption. This was no ordinary volcanic eruption. This was the largest eruption in Earth's history, so massive that its effects literally changed the planet, triggering a second mass extinction event that wiped out more than 75% of all marine species and 90% of all terrestrial vertebrate species. Life would never be the same. So, where did this mega eruption come from? It came from one of Earth's ancient supervolcanoes. It might seem like a contradiction, but volcanoes can actually help us predict what tomorrow will look like. That's because they preserve a detailed record of past events, including details about their frequency and magnitude, which allows scientists to use the geologic record to model how future eruptions might play out. In fact, a team of researchers led by University of Michigan paleoclimatologist Professor David R. McCaffrey recently used geological evidence of past eruptions to simulate future ones. Their findings were recently published in the journal Quaternary Science Reviews, and according to their models, there's a 6% chance of a massive eruption tomorrow. Let's take a look at why. Volcanoes are rated based on how tall they are, how wide their summit craters are, and how big their historical eruptions have been. Most volcanoes are classified as cinder cone or composite volcanoes, but once in a while, a volcano reaches truly gargantuan proportions. These are the volcanoes we call supervolcanoes. There are 12 known supervolcanoes around the world today. They include some of the most well-known volcanoes like Mount Vesuvius, the site of the destruction of Pompeii, Krakatoa, the infamous Indonesian volcano, and even Yellowstone, which may or may not actually be one single giant supervolcano made up of 3 smaller volcanoes. Yellowstone is also the site of one of the most famous super-eruptions in recent history, the eruption of the Huckleberry Ridge caldera. It occurred approximately 2.5 million years ago. The eruption unleashed roughly 2,800 cubic kilometers of ash and pumice onto the North American continent, burying parts of the region under more than 6 meters of debris. The eruption column, the cloud of gas and solid matter rising up from the volcano, reached heights of over 50 kilometers, and the blast radius extended more than 300 kilometers from the volcano. In other words, if Yellowstone erupted again tomorrow, much of Montana and Wyoming would be buried in ash, and large parts of the American continent would become uninhabitable due to falling ash and the resulting climate disruption. But while everyone is afraid of Yellowstone erupting tomorrow, the truth is that it's already happened before, and it won't happen again for at least another 100,000 years. In fact, that's the thing about predicting future eruptions. We don't know exactly when they'll occur. We can only estimate based on how often similar eruptions have happened in the past. And we can estimate how often similar eruptions have happened in the past by studying the geological record. And it turns out that the geological record preserves a surprisingly clear signal of past super-eruptions. That's because super-eruptions don't just release huge amounts of carbon dioxide and sulfur dioxide into the atmosphere, which leads to global cooling, but they also leave behind physical evidence on the land. Calderas form when the magma chamber below a volcano empties during an eruption. If the roof of the magma chamber collapses after the eruption, a large lake may form in its place. Ash and pumice can travel thousands of kilometers from the volcano and settle out on surrounding lands. And tephra, solidified pieces of rock ejected from a volcano, can blanket entire regions. All of these features can persist in the geologic record for millions of years, providing a paper trail for scientists to follow. In the case of Yellowstone, scientists were able to use ice core records to reconstruct the history of past eruptions. By counting the layers of ash deposited in the ice sheets, they found that the interval between eruptions has ranged from 500,000 to 800,000 years, with the average being about 640,000 years. So why is this information important for understanding what will happen tomorrow? Well, for starters, we've been living in the aftermath of the largest of these events, the one I described at the start of the video. The event I mentioned is called the Deccan Traps event, named for the Deccan Traps region in India, where the remnants of the eruptions are preserved today. Researchers have estimated that the total volume of material ejected during the entire eruption sequence was somewhere between 1 and 3 million cubic kilometers, making it the largest known eruption in Earth's history. Deccan eruptions occurred over a time frame spanning hundreds of thousands of years and created a layer of flood basalts over much of the Indian subcontinent. Flood basalts are extensive outpourings of lava that form when magma extrudes out of fractures in the Earth's crust. Basalt is a dark-colored igneous rock that forms from the rapid cooling of magma, rich in magnesium and iron. The Deccan Traps themselves are still a subject of intense study and debate. Estimates for their thickness vary from 500 meters to more than 2,000 meters, and the amount of material they're made of varies from 1 million to 3 million cubic kilometers. We don't even know for sure how long the eruptions lasted. Estimates range from 30,000 to 1 million years. One of the biggest questions scientists are trying to answer right now is whether or not the Deccan Traps eruptions played a role in the extinction of the dinosaurs. According to a recent 2022 paper published in the journal Geology, the answer is probably yes. The authors state, "We conclude that Deccan volcanism made an important contribution to the end Cretaceous mass extinction, acting synergistically with asteroid impact to push Earth into a runaway greenhouse state." In other words, the Deccan Traps eruptions triggered the extinction event, not alone, but along with the asteroid impact. Before the Deccan Traps, Earth's average temperature was about 4 degrees warmer than it is today. But after the traps formed, the average temperature dropped to about 10 degrees cooler than today. Then the asteroid struck and temperatures went up again. The asteroid impact seems to have driven the last spike in temperatures, pushing them 8 degrees above modern levels. But the asteroid didn't cause the initial warming, nor did it cause the subsequent cooling. The Deccan Traps did. So the asteroid and the traps worked together to drive the mass extinction. Not only did they trigger this mass extinction, but they may be triggering the one we're currently living through. Scientists aren't 100% certain that we're currently living through a mass extinction event, but if we are, it's unlike any mass extinction in Earth's history. While previous mass extinctions were caused by asteroids, volcanic activity, or sudden environmental changes, this one is different. According to the International Union for Conservation of Nature, we're causing the 6th mass extinction, or possibly the largest one yet, by burning fossil fuels, destroying habitats, and altering the climate faster than nature can adapt. But here's the interesting part. According to the research led by David McCaffrey, the Deccan Traps may have triggered the mass extinction event 74 million years ago by releasing massive amounts of carbon dioxide and sulfur dioxide into the atmosphere. Sulfur dioxide forms sulfuric acid aerosols in the stratosphere, which reflect sunlight away from Earth's surface, leading to global cooling. Carbon dioxide, on the other hand, traps heat in Earth's lower atmosphere, leading to global warming. In other words, the Deccan Traps may have caused both global warming and global cooling at the same time. In the Lacustrine period following the extinction event, Earth entered a 50-million-year period of global cooling called the Paleogene. But just how much the Deccan Traps contributed to this cooling versus how much the asteroid impact contributed is unclear. To figure this out, McCaffrey and his colleagues conducted new radioisotope dating of multiple samples from the site. They collected samples from 5 different locations in India and used the ratio of isotopes of the element argon to tell how old the rocks were. Argon dating works because when a volcanic rock is first created, It incorporates argon gas from the atmosphere into its mineral structure. Over time, argon atoms decay into potassium atoms, which remains trapped inside the rock. By measuring the proportion of argon to potassium, scientists can determine how old a volcanic rock is. The results of their dating revealed that the major phase of the Deccan Traps eruptions began about 66 million years ago, just before the asteroid impact. Using this information, the team developed a new model to better understand the sequence of events that unfolded. First, the Deccan eruptions started. They released large amounts of carbon dioxide and sulfur dioxide into the atmosphere, which led to a global temperature increase and then a decrease. Then the asteroid hit. This triggered another release of sulfur dioxide into the atmosphere. Because the asteroid impact occurred during the middle of the eruption, it enhanced the cooling effect that had already been set in motion by the Deccan Traps. Together, the two phenomena caused temperatures to drop back down again, wiping out most of Earth's species. Now, this isn't the only model out there. Other researchers have suggested that the asteroid impact was actually the main driver of the extinction, not the Deccan Traps. Some studies argue that the timing of the mass extinction predates the onset of the Deccan eruptions. So how do we know whose model is right? The answer, unfortunately, is that we don't yet. But according to McCaffrey, this study is a step in the right direction. Ultimately, we need to better understand the timing and duration of the Deccan Traps eruptions in order to accurately model how much they contributed to the extinction of the dinosaurs and how much they may be contributing to our current extinction event. So what does this mean for tomorrow? Well, according to McCaffrey's work, we could see a super eruption tomorrow. In fact, he estimates that there's a 6% chance of it happening. But the good news is that it probably won't be as severe as the Deccan Traps. That's because the Deccan Traps eruptions were so huge that they effectively reset Earth's thermostat, drastically changing the trajectory of life on Earth. Eruptions of the same scale are unlikely to happen again anytime soon, but small ones are a different story. McCaffrey estimates that there's a 10 to 30% chance of a small to moderate eruption tomorrow, which could affect regional climates for a few decades or centuries. Of course, if a supervolcano did erupt tomorrow, the consequences would be disastrous. But the truth is that they're already a part of our past. Studying them helps us understand what drove the evolution of life on Earth and may help us predict what disruptions we might face in the future. Thanks for watching this episode. I'm the host. This series was made possible by our patrons. If you'd like to get early access to these videos and get your name added to the credits, you can go to our support page.